In this video, we'll look at a collision in 2 dimensions. We have ball 1 that hits ball 2. Ball 1 is traveling at 2 meters per second, has a mass of 0.25 kilograms. Ball 2 is at rest with a mass of 0.4 kilograms. After they collide, they bounce off each other. Ball 1 has a velocity of 1.5 meters per second, and that occurs at a 45-degree angle. And ball 2, we need to find its velocity as well as the angle that it bounces off of, so that this angle right there. Okay, so to solve this problem, we need to remember that momentum is conserved when the system is isolated. Isolated means that there's no net force, no external net force acting on the system. So if this is an isolated system, we can assume that the momentum initial equals the momentum final. Not only that, what we're looking at specifically with 2 dimension is that the initial momentum in the x direction is equal to the final momentum in the x direction, and the momentum in the y direction initial is equal to the final momentum in the y direction. So that's what we're talking about when we're thinking about 2 dimensions. So let's go ahead and start with this first part here. So I'm going to write Pix equals Pfx. So here we're looking at the horizontal or the x-axis. And we remember that momentum of an object is the mass times velocity. And now we're only looking on the horizontal dimension here. So we're going to have m1, the mass of ball 1, times the velocity of ball 1. And that's the only thing moving. Ball 2 is not moving, so I don't need to write anything for ball 2. And then after the collision, they're both moving in the x direction. So I need to take that into account. So the mass of ball 2 times the, and here I'm looking at the horizontal component. So I'm looking at the horizontal component, and there are 2 components, the horizontal and the vertical. So I'm looking at the v2y, and when I put this apostrophe, this prime here, I'm talking about the final momentum here after the collision. So this will be this will be 2x actually, 2x prime. So this is telling me that it's in the x direction, and the prime is telling me, the apostrophe is telling me it's after the collision, plus ball 1 is also moving at an angle and also moving horizontally. So that's m1 v1x prime. Next, I'm going to substitute my numbers. So m1 is 0.25, has a velocity of 2, and m2 has a mass of 0.4, and we're looking for v2 in the x direction prime after the collision, plus m1 has the same mass, 0.25, and a horizontal has a horizontal component, which is going to be right here. So this is going to be v1x prime, and also has a vertical component, v1y prime. So now we're going to have to take a little detour here and figure out what is the value of the horizontal component of v1 prime. So to do that, we're going to have to do a little bit of trig. So I'm going to kind of redraw that triangle there. Okay, so here's my triangle. I know this side is 1.5, and I'm looking for this side right here, so the v1x prime. Okay, so, and here's my theta, which I know is 45 degrees. So this is adjacent over hypotenuse, so I'm going to be using cosine. So cosine theta is equal to v1 prime x divided by 1.5. v1 prime x will equal, multiply 1.5 on both sides, I get 1.5 cosine, and we know it's 45 degrees. 45 degrees. If I multiply that all out, I get 1.06 meters per second. Okay, so I'm going to substitute that over here, 1.06 meters per second. Okay, and then now I'm going to calculate on my left here 0.25 times 2 is 0.5, so I got 0.5 is equal to 0.4 times v2x prime. So using our trig here, we know that that is going to be equal to v2 prime cosine theta, okay, because we're dealing with adjacent over hypotenuse, plus 0.265. Okay, so I'm going to move the 0.265 to the left, and I get, and then also divided by 4. I'm going to divide by 4, and then on the left-hand side I get 0.5875 is equal to v2 prime cosine theta. Okay, so I'm going to just kind of bracket that because I'm going to come back and use that in a little bit. Okay, so now I'm going to look at the y. I'm going to look at the on the y-axis. We know that the initial total momentum on the y-axis is equal to the final momentum along the y-axis. And initially, there's no motion in the y-axis. So on the left-hand side, that's going to be 0. And on the right-hand side, we're going to have the mass of ball 1 times the velocity of ball 1. But now we're looking at it in the y direction, and prime after the collision plus m2 v2y, and then also prime for after the collision. Now I'm going to substitute in the numbers. m1 is 0.25. The velocity of v1y prime is also going to be 1.06. And the reason for that is because, let me go ahead and write that up here. So v1y prime is going to equal 1.5 sine 45. Okay, so why sine? Because v1y prime is opposite of the theta, so it's going to be, we're going to have to use sine. And if we calculate that, we also get 1.06 meters per second. Okay, I'll go and bracket that because we're going to use that. And the reason that's going to be the same as this number right here is because that angle was 45 degrees. Okay, so back to our momentum here. Then m2 is 0.4 kilograms times v2y prime. Okay, so now I'm going to multiply the 0.25 times the 1.06, and then I'm going to divide it by the 4. And then so on the left-hand side, I'm going to get negative 0.6625. And then on the right-hand side, v2y prime is going to be the same as v2 prime sine theta. So sine theta. Okay, because we're looking at the y component, that component is going to be opposite. Let me go ahead and indicate there. So v2y prime, and so this opposite is that theta, so that's why we're going to use that sine there. Okay, so now I'm going to just kind of bracket this because we're going to use that, combine it with the equation above. Before I continue, I just want to make a note about this negative sign here. Why is there a negative sign? The negative sign is because momentum is a vector, and then so we're making the right positive, okay, and then we're making up positive. So the negative here is just telling us that v2y prime is in the negative direction. Next, we're going to solve for theta, this theta right here, this angle right there, in order to find what v2 prime is. So to do that, we're going to combine this equation with this equation. These two bracketed equations, we're going to go ahead and combine these. So we have v2 prime sine theta, and that's going to be equal to, on the right hand side, negative 0.6625, and then at the bottom we have v2 prime cosine theta and 0.5875. So you'll notice that the v2 primes cancel out. Sine theta over cosine theta is tangent, tan theta, equal to, and then on the right hand side we have negative 1.128. And then if we solve for theta, so take the inverse tangent of negative 1.128, we get that theta is equal to negative 48.4 degrees. So our angle is negative 8.4 degrees. The reason it's negative is because it is in the fourth quadrant. So we're measuring the angle. It's going to go this way, and then so here is our direction, our vector, and so that's why it's the negative. The next step is to calculate what is V2, and we're going to use this equation right there. We're going to go ahead and use that equation to calculate V2 since we know what theta is. So now we have 0.5875 is equal to V2 prime cosine, and we have the angle now. It's 48.4 degrees. And I'm solving for V2 prime. So V2 prime is going to be 0.5875 divide cosine 48.4 degrees on both sides. I got cosine 48.4 degrees. And when I do that, I end up with 0.89 meters per second. So V2 prime, the velocity of mass 2 after the collision is 0.89 meters per second, and the angle is negative 48.4 degrees.